Okay, everyone, let's look at exam number 3, test number 3 from the practice exams, and let's get through it. Number 1, the question number 1 from exam number 3, test number 3. Number 1, 2 moles of nitrogen gas are contained in an enclosed cylinder with a movable piston. If the gas temperature is 250 Kelvin, and the pressure is 1.1 times 10 to the 6 newtons per square meters, what is the volume? R is 8.31 joules per moles per degree Kelvin. So basically the argument, you guys, proceeds as follows. For number 1, we are looking at PV equals nRT, the universal gas law. And we want to find the volume, just divide by P on each side. And we have this. So, okay. PV equals nRT, V equals nRT over P. They told us a few things. Let's do what they told us. They told us there were 2 moles of the gas. 8.31 is R, the universal gas constant. 250 Kelvin, you have to have the temperature in Kelvin, is the T. And the pressure is 1.1 times 10 to the 6th pascals, or newtons per square meter. When you do this, you will find that V is 0.0038 meters cubed. So we have that. Let's look at the problem 2. So let me quickly just verify something very quickly if I could. That, of course, is 2.83 times 10 to the negative 3, if you're going to write in scientific notation. 2.83 times 10 to the negative 3 meters, or forgive me here, let's see. That's not actually the answer. The answer is 3.78 times 10 to the negative 3. And it rounds to this roughly. So that's about, the way the options you had is about roughly 3.8 times 10 to the negative 3 cubic meters. In the answer key, they got 3.78 times 10 to the negative 3 cubic meters. Okay, just to kind of make a note of that. Number 2, we need to be careful about this. I originally did not write this down correctly, basically in a number of ways. But so let's look at the right way this should be stated, and then let's make the solution to it. Number 2, a sample of a monatomic ideal gas is originally at 300 Kelvin. What is the final approximate temperature of the gas if the pressure is tripled and volume is increased to 6 times its initial value? Well, look, there's a number of ways to do this, and let me let's be extremely careful about how this should play out. Well, the way I wrote it in the solutions, in the initial solutions, is not correct based on how this question is asked. Let me answer this question. So it's not correct the way I wrote in the initial solutions, but I am going to show you the correct way, and we do have scrolled at the end of the videos 2 different interpretations of the question, or at least 2 different ways the question could be asked with different values. So you're going to get different answers. The way I asked the question, I simply did not solve it correctly. It could be asked, there could be 2 different ways to ask a question like this with some of the numbers that are present, and you get 2 different answers. But I did not approach it correctly. So let's kind of look at it the way it's explicitly written right here. If they are asking you, a sample of a monatomic ideal gas is originally at 300 Kelvin, what is the final approximate temperature of the gas if the pressure is tripled and volume is increased to 6 times its initial volume? our gut feeling on this should be pretty strong, or at least should lead us to some decent common sense conclusions that can happen. 1 second, please. So, I mean, what we could say, guys, there's a lot going on here. If the pressure at the end of the day is triple what it was earlier, and not only is it triple what it was earlier, but the volume is 6 times what it was earlier. For something to have a big volume, for you to be able to maintain pressure, there's a lot of work that has to be done. There's a lot of energy that has to be there that wasn't there before. There's so much volume that has to be covered, and you still have a pressure that's 3 times what it was earlier. So if you can make the volume very big, and if the pressure is big also, just to be able to have that kind of pressure over such a big volume is indicative of there being, there has to be a lot of kinetic energy in the particles. And the kinetic energy is associated with the absolute value of temperature. If you're going to make, there's a number of ways I guess you could go here. Let me kind of, again, there's just a number of ways we can go here. If you're going to say PV equals nRT, I'll give you like a quick look at this. I would say, look, if the pressure is tripled, and it's tripled not in the same volume, but over a great big volume, relatively speaking, wow, the temperature not only has to be great, like for 3 times the pressure, it really has to be great. 3 times 6. It's got to be 18 what it was earlier. If you're talking about the initial temperature being 300 Kelvin, it's indicative of the average kinetic energy of the particles. The particles to have 3 times the pressure that they had earlier against the walls, and the walls to be essentially much further apart, the kinetic energy is not just 3 times more, and not just 6 times more, but 3 times 6 times more, 18. And that's where you're getting this. This is what it would have to be given the way the question is asked. And I failed to mention that, but that's this. So let's do this a little bit. Let's play this game a little bit. Let's see what we can say about it. How would you actually reach that conclusion maybe in another way? Well, this is of great significance. Okay. You've got a situation where the pressure is 3 times what it was, in addition to the volume being 6 times what it was. And that's going to be associated with a particular new temperature. We'll call it T prime. The original situation was PV equals nRT. Divide these two, and the ratio is 18 to 1. Divide these two, and the ratio is T prime over T. Multiply by T on each side. T prime is 18 times T. We said the original T was 300. And that's where we're getting this answer, you guys. That's where we're getting that answer. Period. End of the story. It makes sense. There has to be great kinetic energy on average in all those particles. You didn't increase the number of particles, which would, at a particular temperature, if there's a lot of particles, that's going to contribute to more pressure. You didn't do that. It's the same amount of particles. Yeah, but you made the volume through which those particles have to travel 6 times the size of what the volume was earlier. And the pressure is still 3 times what it was when it was in a more confined space. The only way that can happen is with great kinetic energy, which is indicative, kinetic energy is directly proportional to the absolute value temperature. So if you're talking about the kinetic energy on average being 18 times what it was earlier? Yeah, it's indicative of the temperature being that as well. The other way you could have done it is that the way the question, that's it, period. That's the way that question would get answered if I kept the original wording of the question. If I had changed that and said that the volume just doubled, it was not made 6 times as much, but it was made double as much, then it would be 2V times 3P equals NR, the T prime business again, NR, the T right here, and everything cancels except for this. It's basically the same game being played. T prime is 6 times T. T prime is 6 times 300. Here's where the 1800 Kelvin comes in. That would be the right answer if the volume was only made twice as big, not 6 times as big. So that should be in the notes as well. It's awkward that it happened that way, but perhaps gives us a way to look at this even further. So it would be 1800 Kelvin if the volume was doubled, not made larger, by a factor of 6, but made larger by a factor of 2. Okay, and then that would be the case. So it depends how it's going to be worded, guys. That was my fault how that happened. You see it right here, and the way I have already sent this out to people who are my students, with whom directly I work, but also you'll see this scrolling in the films as well. Let's go to number 3, you guys. Let me erase this and take it from there. Number 3 pertains to radiation. Number 3, radiation. There are 2 identical objects. Object A has a temperature of 50 degrees Celsius, while object B has a temperature of 190 degrees Celsius. What is the ratio of the power emitted by object B? What is the ratio of the power emitted by object B to the power emitted by object A? P sub B divided by P sub B. Ignore power absorbed by each from the environment. Shouldn't be too bad, guys. We're talking about a situation here. Again, all of this is going to be scrolling, guys. So you'll be able to see at the very end of the videos, you'll be able to see the questions and be able to see the solutions written as well. Essentially, they're saying power associated with radiation is the emissivity constant, sigma, emissivity constant E, then you got sigma, you got A, you got T to the 4th. It's got to be an absolute value temperature when you're talking about this kind of stuff. So P sub B divided by P sub A, epsilon sigma A, let's see what we got here. They are talking about 190 degrees Celsius. 190 degrees Celsius plus 273, you're always adding 273.15 to any Celsius temperature to get the Kelvin temperature. Let's just say 273. We'll keep it. We should be in the ballpark of where we need to be. 273 plus 190 is 463. The other one is saying, okay, that was the 190 degrees, 190 degrees Celsius. The other one's 50 degrees Celsius. So 50 plus 273 is 323. And that's to the fourth. Well, here we go. Cancels. All, one time one. We got this. At the end of that song and dance, guys, that ratio is going to be 4.22. That's 3. Let's look at number 4. Waves on a string. A string of mass small m is under tension, and the speed of a wave in the string is v. What will be the speed of a wave in the string? What will be the speed of a wave in the string, the same string, if the mass of the string is increased to 5m? Earlier, the mass of the string was just m. Now, let's increase the mass of the string to 5m. It's not really the same string, it's a different string. But with no change in the length. But the tension is doubled. How does that work? Well, V equals the force tension in the string divided by the linear mass density of the string. So we've got this. Let's talk. Let's say V prime is the second situation where the string is made 5 times the mass of what the original mass of the string was. And let's take a look at the other. So there's a number of ways to go. Let me kind of just write it like this. This is the new scenario. You've doubled the tension compared to what it was, and the linear mass density, forgive me, the linear mass density is 5 mu. The other one is the way it originally was, and it was just, I guess you got to have a baseline here somewhere. We got to here. All right, sounds good to me. V prime over V is the square root of this divided by the square root of that, which is 2ft over 5 mu divided by ft over mu. Now we're going to use all our skill in the mathematics for some of the basic operations that we got to do. The ratio of two roots is the root of the ratio. So you got this ft over mu. Well, I mean, the mu pops up. ft and ft cancel. You got a 2 right here. The mu flips over like this, and you got a 5 on the bottom. And you're looking at, at the end of the day, that's what you're looking at. Here's another way to look at it, actually. This is f sub t over mu. This is f sub t over mu. They completely cancel, and you got 2/5 left over. You can look at it like that too. That's that. V prime over V equals the square root of 2/5. V prime, what is the new velocity compared to the original velocity? And that's it. And that should be consistent with among the choices of answers that you have to be able to look at where this is going to go, you guys. Okay, that was number 4. Number 5. Number 5, the intensity of a spherical wave 20 meters from the source is 1,500 watts per square meter. What is the intensity at a point 9 meters away from the source? Okay, good enough question. So for this one, well, look, our gut feeling should be the closer you are to the source, the more intense things are going to be. So we got that kind of under control. What they're saying here is, as I said, the intensity of a spherical wave 20 meters from the source is 1,500 watts per square meter. What is the intensity at a point 9 meters from the source? Well, if it's a lot close, if it's somewhat closer, definitely closer, somewhat closer, let's say even a lot closer, the intensity is going to be more than 1,500 watts per square meter. I mean, the way you want to look at it is they're saying, if you're going to talk about the intensity associated with a spherical wave, you're talking about the power divided by the area that is traversed, that is penetrated, I guess, to get to there. So you're looking at this situation. If that's the case, let's compare the two places. This is the scenario with where r is smaller, where you're close. This is a scenario when you're closer. We'll call that I sub 2. This is the original scenario when you're further away, and you're basically talking about p over 4 pi r, r sub 2 squared over p 4 pi r sub 1 squared. Okay. Well, when you do this, there's a lot's going to happen here, guys. At the end of the day, this ratio, all the cancellation and all the things that are going to take place are telling us we're getting to here. We're getting to here, and yeah, well, that's what we got here. The p's cancel. The 4 pi r sub 1 squared flips up. The 4 pi's cancel, and the r sub 1 squared is here, and the r sub 2 squared is here. Well, what does that mean? Well, it means a lot of stuff. I mean, at that point, if I want to find what I sub 2 is, I basically can just go, okay, let's go I sub 2. Let me multiply by I sub 1 on each side. Let me, if I got this, as we're talking about it, guys, if we got this, and it came from, here's the original look, you go here, and then you're just going to take this and divide it by that to get this. The only thing that's going to, the 4 pi's are going to go, the p is going to go, the p is going to go, the 4 pi is going to go, the whole lot of stuff's going to go, guys. So what we have here is I sub 2 is equal to I1 we got this. What does that mean? Well, it means I sub 2, the original is the 1,500 we were talking about. The R1 was 20. So let's, the R1 was 20. So we're going to square that. The R2 is 9. Going to square that. And yeah, it comes out pretty straight when you do that kind of thing. So let's see. Play the game here, that's 400 over 81. It's in the ballpark of 5 over 1, 5 times the intensity, in the ballpark of 7,500 or so. What it comes out to here is 7,407.4 watts per square meter. We said it was going to be somewhere in the ballpark of 5 times, 400 divided by 81 is about a ratio of 5 to 1. Something a little less than 5 times 1,500 should be a little less than 7,500. And that's what we got for an answer right here, guys. Okay, that was, thus far we've gone 1 through 5. Let's go to 6. Let's erase and proceed. Just check the sound quality, guys. The sound appears to be going pretty well. Okay. Number 6. Number 6, a fire truck going at 35 meters per second with a 900 hertz siren is approaching a car which is moving in the opposite direction in the other lane. So they're basically coming toward each other in some sense, but in opposite lanes, of course. The car is going 15 meters per second. What is the frequency, F sub O, experienced for the person in the car? It's a great question. So, what's going to be experienced is F sub O, what the observer sees or experiences. This is the source, if the source were just standing still, what's going on there. This is the velocity, the magnitude of velocity of sound in the particular medium. And V sub O is the velocity of the observer. If the observer is going toward the source, it's plus. If the observer is going away from the source, it's minus. Here's again the velocity of sound in that particular medium, or at least the magnitude of the velocity of sound in that particular medium. And this is, if the source is moving toward the observer, then there's a minus. If it's moving away from the observer, it's a plus. Here, if the observer is moving toward the source, it's plus. And if it's moving away from the source, it's a minus. So, yeah, just watch out for the plus, minus, minus, plus, how that works out. They are asking the question. And we know the answer. I mean, we can find the answer. We're told the fire truck is doing 900 hertz. We are told that the speed of sound is 343 meters per second. And the observer is going toward the fire truck, so it's plus. The fire truck is going toward the observer. 343 is still the V here. It's going toward the observer, so if it's going toward the observer, it's going to be a minus right here, and that's going to be 35. This maximizes what you're going to see. If you're the observer and you're going toward the source, plus makes the numerator big, and minus makes the denominator small, which makes the ratio a big answer. It makes sense that if the fire truck is going toward the person, they're going to experience the sound waves more frequently. So this is the mathematics that is being done. Look at it. Let's see where we are. And there it is, guys. That's number 6. Number 7. So, number 7, you guys. Number 7. Using the exact same speeds as in problem number 6 that we just did right here. above, using those exact same speeds as in problem number 6 above and the same siren frequency, what is the frequency experienced, FO, for the person in the car after the fire truck and car have passed each other? Now, after they've passed each other, guys, it's a different dynamic. It's, again, much of the data is the same, if not all of it. You know, you're saying, okay, well, let me use, for number 7, let me use this. You know, when I'm dealing with this stuff, let me go here, let me use this. You know, whenever I'm encountering something similar to this. And you're going to say, let's talk about it. Well, you know, this is kind of interesting. FO equals the 900 we're talking about, again. But here's the difference. Well, I mean, 343 and 343 remain the same. That's the speed of sound in air for our purposes at particular temperature and other things under consideration. That's fine. But when they pass each other, the observer is not going toward the fire truck anymore. It's leaving the fire truck. It's leaving, it's going away from it. So it's not plus 15, it's minus 15. The fire truck at the same time is not going toward the observer, it's leaving it. So then it becomes plus 35 here. Our hunch is that it's going to be a smaller answer than we had earlier. It's going to be a smaller answer than the 900 that was originally present. Look at the ratios. Just look out what's going on here, guys. Again, look at it, play the game here, guys. Again, I'm using in both number 6 and number 7, so I don't have to write it down again. FO is Fs times the quantity, V plus or minus VO, over V minus plus Vs. And there we go. And we got number 7. Let's talk about heat conduction. And we have talked about how important, I mean, a lot of these phenomena, they have applications, or at least some of the mathematics that's talked about is seen in other areas of physics, I guess you could say. There's like an analogy, how heat is conducted by conduction. How that looks a lot like what happens in electricity, how conduction takes place. So let's take a look here. Problem number 8. The ends of a cylindrical steel rod are maintained at 2 different temperatures. That's the only way there's going to be a flow of heat, you guys, a net flow of heat. They got to be at 2 different temperatures. The ends of a cylindrical steel rod are maintained at 2 different temperatures. The rod conducts heat from one end to the other at a rate of 80 joules per second. At what rate would a steel rod 5 times? It's the same material now, guys. At what rate would a steel rod 5 times as long and 6 times the diameter conduct heat between the same 2 temperatures? That's an interesting question in its own right. Let's talk about it. Power. Now here the Q means something different. Q is the amount of heat energy transferred, per unit time. Power is heat energy per unit time. Energy per time pertains to power. There is a constant pertaining to what the material looks like. That's K. There's A. There's delta T, which is Kelvin temperature, differential. And L is the length. The more area, the easier heat can be conducted. The less area, not as much heat can be conducted. Contrary to that, so it's a direct relationship with area. More area, more heat conducted. For L, it's a different dynamic. If it's longer, it's harder to conduct heat. It's got to go through a lot. If it's shorter, it's easier to conduct heat. If there's a big temperature differential, it's easier for there to be a kind of conduction of heat. K is a constant. The conduction of heat is directly proportional to area, cross-sectional area, directly proportional to temperature difference, and inversely proportional to length. That's about it. I mean, that's kind of where we're looking. I mean, you're going P sub 2, P sub 1, Let's talk about A2. Delta T is the same. I think they said keep the same under consideration regarding that. And here it's K A1 delta T well, okay, interesting. Again, they said the delta T would remain the same regarding this. Between the same two temperatures. Well, between the same two temperatures, the difference in temperatures between the two is delta T, so it's the same. If this is the case, the delta T's are going to go, the K's are going to go. This flips over, and you end up getting and this is L1. Yeah, direct relationship, inverse relationship. That's why the subscripts are altered. And that's it. I wrote this differently. I think I put A2. I put A2 over L2, A2 over L2, and then L1 over A1. That's absolutely not an issue. But let me kind of stay consistent with stuff I've done. So this right here, you guys, all that right there, let's put it up here, I guess. Let's go up here, and that's just going to be, at the end of all that, the P2 over P1. P2 over P1 is going to, like I said, this is not an issue. The mathematics is identical. It's just a question of a little bit of mathematical gymnastics here. That's fine. I mean, look at that. They're the same fractions here. Let me just stay kind of consistent with what I've done, I guess you could say. Okay, so let me... okay, you got to be kidding me. I think I went back to this, so let me just make sure, guys, that shouldn't be an issue. At what rate would a steel rod 5 times as long and 6 times the diameter? Yeah, I mean, okay, they do this. They meaning me, I did this. I probably just as easily could have stayed at that. So they both mean the same thing, guys. Let me... You know, I just think this is not a big deal either way, guys, because it's the same stuff. But let me stay here. Let me compare the areas. If the diameter is 6 times, if the diameter in the second scenario, if the diameter is 6 times what it was originally, that means if the diameter is 6 times what it was originally, then the radius is 6 times what it was initially. So that's something. I mean, either way here, the way this is, yeah, I don't like the way I wrote some of this, but it's still reasonable. It still works out. Let me just let's talk about it. If the diameter is 6 times what it originally was, so 6 times what it was here, the diameter is 6 times what it was here, the radius is 6 times what it was here. So this is 6 times the radius of what the other one was. And the other one's just this. And if the length, the length is 5 times longer than what it was originally. You got this, and that's really the way the whole argument's going to proceed. The original length L1 is L1. Original length L1 is L1. I'll call it L. The other one is 5 times that. You got this, and I think you know what's going on, guys. You go here. This is 36r squared. This is 1r squared. This is 36 over 1. This is 1 over 5. So 36 over 1 times 1 over 5 equals 36 over 5. It goes in here. That ratio is 7.2. So P2 over P1 is a ratio of 7.2 to 1. So what's the power? You know, what power is transferred? You'd go P2, multiply by P1 on each side. It's 7.2 times P1. It's 7.2 times 80, right? 576, I think. Yeah, so it comes out 576 joules. If you can create those circumstances, the new power, you know, what kind of a power transfer are we talking about? What kind of power is transferred given these circumstances? And we got it. So, right, at what rate would a steel rod 5 times as long, so it's 1 over 5, and then 6 times the diameter, that's 6 squared over 1 squared, you know, so 36 over 5 at the end of the day, guys. 7.2 times the power would be transferred if that maintenance of temperature could be maintained, and can somehow, that's what we would have getting transferred if we had it in those circumstances, if that was the case. That's number 8, folks. Let's go to number 9. Let me erase this and we'll talk about it a little bit. Okay, number 9. 6 moles of an ideal gas initially at 178 degrees Celsius is compressed at a constant pressure of 2 atmospheres to 1/3 its initial volume. What is the final temperature of the gas? So it's compressed at a constant pressure of 2 atmospheres to 1/3 of what its initial volume was. Find the final temperature of the gas when the initial temperature was 178 degrees Celsius. So you got to be careful. Everything's got to be in Kelvin. So when we talk about this, we've been down this road before, guys. We got this. Let's talk. Second scenario. Now, I mean, this is kind of interesting how they go about this, how we want to interpret something, guys. There's 6 moles of an ideal gas. It's initially that much. It's compressed at a constant pressure of this much and 1/3 its volume. Find its final temperature of the gas. We'll say that the pressure initially was whatever it was, and then constantly it's being taken down to 1/3. What's going on as we're changing circumstances? Well, P2V2 equals nRT. You're not changing the number of moles in the gas. And here's another situation. So P2V2 over P1V1 equals nRT sub 2, nRT sub 1. We're also told, in a somewhat of a backhanded way, that the pressures are the same. They started out, the pressure stayed constant. But what happened was, you applied this pressure, you had what you had, and as you continue to apply that pressure, you are changing the volume. At some point, though, the pressure is the same, though. It's a constant pressure being applied throughout. That's not, just be careful if the question's phrased that way, right? So P2 and P1 are just P. The end scenario, the end scenario is pressure P that it's under. It's going to 1/3 the volume that it once had. And that's associated with nR T sub 2. The other pressure is that, and it's just V right here. And this is nR, and they're telling us that it's 178 degrees Celsius. So 178 degrees Celsius, if you add 273 to it, you get 451. So it's 451 Kelvin. So that's what we're looking at. The constant pressure, it was applied, there was a pressure of 2 atmospheres initially, and there's a pressure of 2 atmospheres at the end of it. So that's pretty interesting. How does that happen? Well, it's the pressure 2 atmospheres in all circumstances. Initially, when it was volume V, it was 2 atmospheres pressure. When it's volume of 1/3 of what V is, it's still the pressure of 2 atmospheres. Well, that cancels, the V cancels, and you have 1/3, and then here we go. The N's go, the R's go. You got T sub 2 over 451. Multiply by 451 on each side. Multiply by 451 on each side, and you get, 150.33 Kelvin. Let's see how they wanted this answered. Okay, let's time out for 1 second. This makes sense that the Kelvin temperature is going to be smaller, very much smaller. You cannot have the same pressure existing in a confined area unless the temperature somehow has changed. The temperature, the average kinetic energy of the particles is going to be somewhere on the order of 1/3, because 150.33 is about 1/3 of 451. The average kinetic energy of each of the particles in the gas, once you've compressed it under that constant pressure, the average kinetic energy of those particles, somehow there's some process taking place that they're not telling us about, but there's some process taking place. There is 1/3 the kinetic energy on average, roughly, in the particles after you have compressed the gas to 1/3 of its volume. Yes, the reason for that is if it stayed the same temperature, the pressure would be 3 times as great. And it's not. It's the same, but it's not 3 times what it was. It's not 3 times what it was. It's the same as what it was. So the kinetic energy has to be less. It can get away with having less kinetic energy and maintaining the same pressure because there's less distance to travel to make the collisions against the side of the container. Very important. Very important. So we got this. If that's the way it looks, T sub 2 is 150.33 take the Celsius temperature, take the Kelvin temperature and subtract 273. And what we got is negative 123 degrees Celsius, according to this situation. So both of these are true. What's circled in green, what's circled in red, they're both the same temperature, just depending on how they're going to ask you what the question is, what the answer is. Since they were talking about Celsius from the get-go, they're probably going to stay with the Celsius. Okay? So you look at that. That's number 9. Number 10. Number 10, a mass small m equals 60 kilograms is attached to a spring having a force constant, K, of 2,000 newtons per meter, as in the figure. The mass is displaced from its equilibrium position and released. Its frequency of oscillation in hertz is approximately what? Okay, not too bad. We will just kind of go with what we know of the formulas that we have. So let's see here. We got omega, the angular frequency will be the square root of the ratio K over M. Omega is 2 pi f. So omega is 2 pi f, so we got to have that in the back of our mind when we're dealing with a lot of this stuff. Watch out. I mean, they're directly proportional to each other, two different entities. They use the word frequency, just be careful. Omega is 2 pi f. Divide by 2 pi on each side. It's 1 over 2 pi times K over M, which is simply 1 over 2 pi times K over M. It's got to be MKS system of units. Don't just randomly plug in numbers. Plug in the numbers when it's MKS system of units, and the equations are obviously correct. The equations have to be correct, of course. F is 0.919 hertz. Okay, simple as that, guys. That's the answer for that one. That's number 10. Let me see if I have room. If not, we'll do the erasing, I guess. But let's see. Have a look here. That should be all right. For number 11, if y equals 20 sine of the quantity 200x minus 300t SI units, the wavelength of the wave is what? And the options that you're given here is they're not really asking. They're asking for the answer in terms of in terms of pi. I mean, there's pi in there, I guess, and they keep it there, so that's fine. That makes it a little easier to look at when we're doing some of this stuff. They are telling us. Let's have a look here. They're telling us that we are given this wave equation for a traveling wave. Y equals a sine (300t). Yeah, I mean, what is that? Well, the amplitude is 20, according to the way this is written. This is what they gave us something looking like this, and we're saying, okay, if it's looking like that, how much, do we know what A is at least? Yeah, we know what it is. The way that they write the problem, we know what it is. We've got this. Okay. We do know, kind of in the back of our mind, the wave number is 2 pi over lambda, which means, k equals 2 pi over lambda, multiply by lambda on each side and divide by k. That's kind of interesting. Yeah, absolutely it's interesting. So we know that this right here, maybe a better way to even do this, guys, is for me to erase this and put an omega t right here, erase this and put a kx right here, so we know who's who. Well, if that's k, that's k. If that's omega, that's omega. So k, and I hate erasing this stuff, guys. It doesn't come out as clean sometimes, but maybe that's a little more general form for us to look at. K is 200, omega is 300. K is 200. Yeah, then we got 2 pi right here. At the end of the day, guys, that just implies that lambda, the 2 and the 200 cancel, and you got pi over 100 meters. Using what they gave us. And that's number 11. That's number 11. So the wavelength of the wave is that. Let's go to number 12 and see what we can say. Okay, folks, let's look at number 12. Write the equation of a wave traveling along the positive x-axis with an amplitude of 2 meters, a frequency of 250 hertz, and a speed of 50 meters per second. Okay. You sort of have to work backwards, I guess, to do this. So let's see what we can say about it. We know a number of things. I'll figure out how they want to talk about it, I guess you could say. Y equals, it's traveling along the positive x-axis. Okay, we'll cross every bridge as we need to, I guess. We got A right here, amplitude, sine of kx plus or minus omega t, look at something like that. A is A, sine is sine, k is 2 pi over lambda, omega is 2 pi ft. Omega is just 2 pi f, and then you throw the t on there. Omega is 2 pi f, so you throw the t on there. We're looking at something like this. The fact that it's going along the positive x-axis, we're going to use the minus to actually get there. So what happens is, they say a number of things to us. Let's let me just make sure I'm speaking their language, I guess, guys. Write the equation of a wave traveling along the positive x-axis. So we're going to use a minus inside that argument. If we're going to go along the positive x-axis, we use a minus inside of that argument. It has an amplitude A of 2, a frequency of 250, and a speed of 50. Okay, so it has an amplitude of 2 meters, a speed of 50 meters per second, and a frequency of 250 hertz. Okay. Sounds good. We could say a number of things. We know that K is equal to 2 pi over lambda. We know, forgive me, yeah, we know a number of things actually. We could say we know that K is 2 pi over lambda, okay, in the formulation here. We know that omega is 2 pi f. If you take omega and divide it by k, 2 pi f divided by 2 pi over lambda, you get lambda f. You get v. That's kind of neat. That's definitely of interest. I mean, if that's the case, and we said v is 50 meters per second, v is 50 meters per second. So omega over k equals 50 meters per second. So let's talk about a number of things here. Let's see what we can put in place of something to figure out what's going on here. Well, I guess I could solve for k, multiply by k on each side and divide by 50. Multiply by k on each side and divide by 50. And then omega is 2 pi f over 50, right? And yeah, but they already told us that f was 250. Two times 250 is 500. 2 times 250 is 500. 500 times pi divided by 50. K is 10 pi. So wait a minute, maybe I got some ideas here. Y equals 2. They just told us the amplitude was 2. 2 pi over lambda is what K is. Well, we already played that game a little bit, or at least we played it enough. We know that K is 10 pi, so put an X here. It's going to the left. I'm sorry, it's going in the positive X direction, so it's a minus. 2 pi ft, 2 times 250 is 500. These are all radians. 2 times 250, or inverse radians, right? Or radians per second. 2 times 250 is 500. And we got that. I think that's it. I mean, there's... And there you go. For 13, for 13, waves on a string. A string of length capital L is under tension, and the speed of a wave in the string is v. Sounds kind of familiar. That's all right. We can do it again. Waves on a string. A string of length capital L is under tension, and the speed of a wave in the string is v. What will be the speed of a wave in the string if the length is increased to 9 capital L from 1 capital L? made 9 times the size, but with no change in the mass or tension. In other words, the linear mass density is 1/9 of the original value now. Yeah, the mass of the string, this is very important here, but with no change in the mass. No change, not in the mass density, no change in the actual mass of the string. In other words, you got a string that has 1/9 the mass density that it had earlier. It's 9 times the length of what it was earlier, but it's the same mass as what it was earlier. That's what they're trying to say here, guys. Let's take a look. All right, well, let's see what kind of an argument they want to put forward for this whole process. They're basically saying if the mass is the same in both circumstances, there is a linear mass density originally present of mu. What is it? Well, the original mass density originally present was, it was a mass m associated with a length L. In the second scenario, it's the same amount of mass of rope, but the rope is less dense because you need 9 times the length of rope to have the same mass. It becomes this, which is the same as 1/9 times m over L, which is 1/9 mu. So I guess what we're talking about is, if you're going to talk about it, we can. And I go about this in a little different way. Again, the big thing is the mass density does change. The linear mass density does change. The mass of the rope remains unchanged, but you got a rope that's 9 times the length of what the original rope was. Even though it's 9 times the length of the original rope, its mass is no less or no more than what the original length of rope was. Even though there's 9 times longer, there's 9 times the length of rope. Nevertheless, it's the same mass. So it's 1/9 the mass density. So if it's the same mass over a longer length, do the math. It's 1/9 m over L. Well, 1/9 of this is 1/9 of that is that. So you're looking at this situation. You're looking at this one and you're looking at this one, and we'll see how that plays out. Okay? Just trying to look at how we actually looked at it. We can say, I don't know, the way I'm not thrilled by the way I did it actually in the notes here, but it's not a bad way to do it. Let me kind of give you another look at it when you kind of look at it. You could say, okay, wait a minute. Don't we know that generally speaking, the magnitude of the velocity along the rope is going to be Ft over mu. And yeah, fine. Can we compare the two? Yeah, let's do so. We got, this is the new scenario, and this is the original scenario. New scenario would be Ft over 1/9 mu. Old scenario is Ft over just mu. The ratio of roots is the root of the ratio. The FT's cancel, the mu's cancel. You got 1/9 on the bottom there. You end up getting this whole ratio is 1 over 9 square root of it. Let me try to understand that. That is not true, actually. Ignore that, please. What we have here is it's going to be the 1 over 9 here is going to go 9. The 1/9 on the bottom is going to be 9 Ft over mu. That's what the 1/9 does. This is Ft over mu. I guess there's a number of ways to go here. Let me opt to go this way. This is identical to that. And the square root of 9 is 3. If you multiply by v on each side, you get this. Numerous ways, I don't know if I can say numerous ways, but there's a number of ways to make the argument. We understand that if the tension's the same, if the tension's the same, but there's a situation where it's simply not as massive per unit length. Not being as massive per unit length is conducive to greater velocity associated with the transmission that takes place. And that is that. Number 14. Intensity. The intensity of the waves from a point source at a distance d from, so here we go again. Intensity. The intensity of the waves from a point source at a distance small d from the source is I. At what distance from the source is the intensity equal to 4 times what that intensity is when it's a distance d from there? When is it 4I? Well, it can't stay where it is. We got to move it. If you move further away, it's going to be less intensity, so it's got to get closer. So how does it become 4 times the intensity? How on earth does it become 4 times the intensity when, at what distance does that happen? So let's just quickly give it a little look here. As we said, intensity. How is that going to work? Well, look, let's just make it pretty clear, pretty obvious. We remember enough about the mathematics that we're going to use that very same mathematics that we remember. We know that I is going to be power over 4 pi r squared. We also know that, okay, that's the case. How are we going to compare these? What's going on here? Well, if I want it to be 4 times the intensity of what it was earlier, the ratio is going to be 4 to 1. Over here, there's going to be power over 4 pi r2 squared. And over here, it's going to be the same power, 4 pi r1 squared. Did I say cubed earlier? It should be squared. Okay. We got this. Yeah, guys, please, let's remember that in the back of our minds, the r1 is the d that was being talked about. Right? So let's see how this all is going to work. I mean, we got this. Yeah, it's a little more clear, guys. All this stuff goes on here. What do we got? We got 4I over I is a ratio of 4 to 1, or just 4. That cancels. This flips upward and goes on top of this. The 4 and the pi cancel. You got r1 squared over r2 squared. Be careful. Look at how this mathematics proceeds. We are told that r1 is d, and r2 is whatever it's going to be, I guess. Let's multiply by r2 squared on each side, and divide by 4 on each side then afterwards. Let's multiply by r2 squared on each side, and then divide by 4 on each side. We've got this. square root both sides. R2, square root of this is d, square root of that is that. If you go half the distance to it, you're there. R sub 2 is 1/2 d. R sub 2 is d over 2. I think I wrote it as d over 2 here. That's, that's not the big deal, but get the answer. Let's make sure we're getting the answers, guys. For problem number 15, we will get to that. Let me erase and we'll take it from there. Okay, number 15 asks us, number 15, a body oscillates with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation x equals 100 cosine pi t. The magnitude of the acceleration in meters per second of the body at t equals 12 seconds is approximately. So there's a mass. There's a mass that is oscillating with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation x equals 100 cosine pi t. So the magnitude of the acceleration of the body at t equals 12 seconds is approximately what? There's, I guess, a number of ways to go here. So they want the magnitude of the acceleration of the body. So that's of interest. We go through a lot of this stuff, and we remember from discussions, by the time you'll have gotten to this, you'll remember discussions in class on this, x equals cosine omega t, v equals negative omega a sine omega t, and acceleration is negative omega squared a cosine omega t. It's easier to look at this through the use of calculus. We've done it other ways in non-calculus based courses, so and we're reaching the same conclusions. We're reaching this as a conclusion. The absolute value of the acceleration is going to be whatever the absolute value is of this. And don't think just because it's a negative here, it's going to be a negative number. It may be a positive number, depending where you are in time when you're doing this. Well, they're asking us, what's going on here? You know, get us an answer here. Well, okay, they're saying, it's a real good question, is what it is. What we can say is, we know what, guys, this right here omega equals pi. And that's going to make the whole thing happen for us. The way this is written, they already kind of gave us the hint on that. Omega is equal to pi. So you got negative pi squared. The amplitude is what's in front of this thing. And the amplitude is equal to 100. So they're telling us a lot. It's already kind of in there in the discussion here, in the initial presentation. So this is 100. You square pi, you get close. You square pi, you get close to 10. 10 times 100 is 1,000. That's negative 1,000 times the cosine of pi times 12 seconds. And this has got to be in radians. The final answer here is in radians. So be extremely, extremely careful when you're doing this. Well, pi times 12, you guys. Pi times 12 absolutely, it's omega times t. It's omega times t, which is pi times 12, which is the same as 12 times pi. Anyway, this is in radians. Make sure your calculator is set to radians. You're going to get it wrong otherwise. Almost for sure get it wrong. The absolute value of the acceleration, if you knock this thing out, should come out to 787 meters per second squared. And that's number 15, folks. 16 and 17. 16, what is the wavelength of a wave? For number 16, what is the wavelength of a wave with a speed of 12 meters per second in a period of 0.25 seconds? Just want you to do a little bit of math, of the mathematical gymnastics and the things that we know. What is the wavelength of a wave with a speed of 12 meters per second in a period of 0.25 seconds? Well, to look at that, we know V is equal to lambda times F, or F times lambda. V equals lambda times F. F is equal to 1 over the period. F is equal to 1 over the period. They told us the period is 0.25. That's 4 hertz. That's 4 cycles per second. 1 over 0.25 is 4 hertz. The V, they're telling us the V is 12. The V is 12. I don't know lambda. They're asking me to find lambda. But we did find the frequency to be 4. 12 equals 4 times lambda, or lambda times 4. Divide by 4 on each side. Three meters. 17. And again, there's some repeats here, guys, as well, but we're okay. We're not doing too bad. Of earlier content, that's okay. Gives us a little bit of practice. Let's go to number 17 then. 17, a bell emits sound energy. Number 17, a bell emits sound energy uniformly. A bell emits sound energy uniformly in all directions at a rate of 9 times 10 to the negative 3 watts. What is the intensity of the wave 40 meters from the bell? So, sound energy sound is indeed a form of energy. A bell emits sound energy uniformly in all directions at a rate of 9 times 10 to the negative 3 watts. What is the intensity of the wave 40 meters from the bell? Well, what we remember is what we will do. When we're doing this, we say, okay, well, 17 is asking, we know this. Okay, sounds good to me. The rate at which sound energy is propagated is this many watts. 9 times 10 to the negative 3. 40 meters from the bell, 4 pi r squared. 40. Wheel and deal with the mathematics a little bit. You square the 40, you get 1600. 4 times 1600 is 6400. 6400 pi into here. It's going to be relatively small, but let's see what we got for an answer. So you plug in like that. And the intensity, again, the units are fine. There's no problem with the units when we're doing this stuff, you guys. Four point 4.48 times 10 to the negative 7 watts per square meter. Excellent. Let's look at 18. Let's see what we got here. For number 18, a car moving at 30 meters per second approaches a stationary whistle that emits a 560 hertz sound. The speed of sound is 343 meters per second. What is the frequency of sound heard by the driver of the car? The car is moving at 30 meters per second. It's approaching a stationary whistle that emits a 560 hertz sound. So it shouldn't be too bad, guys. It should be pretty reasonable. In fact, somewhat easier than some other things we had seen. Okay, so just get a little more chalk, guys. So what they're telling us is things we already know. I mean, we already have this from the past. We have it in our mind. We know how to work this. We've already discussed this. We're just going to follow the same kind of argument that we've already done in the past, and in some ways I guess you could say it's a little bit easier. We got this. Okay, so we're working with this to figure out what we're doing. Pretty straightforward stuff, guys. I mean, at this point, we got this. 560 is the frequency coming from the stationary whistle. The observer is moving toward the sound source. But the whistle is not moving. V sub s is 0. So it's just 343 right here. That is it. That is it. Let me just make sure I'm asking that. Right. A car is moving 30 meters. A car moving at 30 meters per second approaches a stationary whistle. Okay, it's approaching it. That emits this. What is the frequency of the sound heard by the driver of the car? It's a stationary whistle, so it ain't moving. So there's a lot of subtlety here. There's potentially some subtlety. We really need to pay attention. We can't say we don't get something. They tell us enough. We get it. We can do it. So we go here, and we get, which would make sense. The observer is going to encounter, associated with this whole process, this frequency. And that's 18. Let's keep going. Let's go 19 onwards, guys. Excuse me, guys, I got chalk all over the place, obviously, here. All right, folks. Number 19. Number 19, when a force of 80 newtons is applied to a spring, it elongates to 0.1 meters. Determine the period of oscillation of a 50 kilogram object suspended from this spring. So when a force of 80 newtons is applied to a spring, it elongates by 0.1 meters. Determine the period of oscillation of a 50 kilogram object suspended from this spring. So, pretty basic stuff, guys, at this point. They want to know the period of oscillation. So, we got to look out. We got to look out. Omega is 2 pi f. That means if you divide by 2 pi on each side, omega is 2 pi f. If you divide by 2 pi on each side, f is omega divided by 2 pi. The period is 1 over f, and 1 over f is the same as 1 over this, which becomes this. So if you want to know, if you can find omega, go 2 pi over omega, and you'll know the period. That's kind of the end game scenario that you're looking at for problem 19. So let's talk. Omega, and there's a lot can be said here. We're not going to say all that can be said. We do know that omega, based on our studies, omega equals the square root of the ratio k over m, which is equal to the square root of, well, what's k? Well, they're telling me if I give an extra 80 newtons of force, the spring will elongate by 0.1 meters. So force divided by distance. Remember now, let's just talk about absolute values. I'm not going to throw negative signs in here. If you want to find what k is equal to f over x. If f equals kx, if f equals kx, if f equals kx, divide by x on each side, and k is equal to that. Well, this is 80 divided by 0.1. That's where I'm getting this. 80 divided by 0.1. 80 divided by 0.1. M, they are talking about, let's talk about it. Let's see, forgive me, guys. That was a 50 kilogram object that they were talking about. 50 kilogram object that they're talking about. Omega, at the end of the day, is going to be the square root of this. What do we got here? 80 divided by 0.1 is 800. 800 divided by 50 is 16. Okay, that comes out pretty conveniently, doesn't it? The square root of 16 is 4. That's 4 radians per second. That's omega. True. Now what? Well, F, we said F is omega over 2 pi. So F is omega over 2 pi. Omega is 4, right? Omega is 4. Omega over 2 pi. Here's 2 pi. The 2 and the 4 cancel. You got 2 over pi hertz. 2 over pi hertz is equal to F. We also know that T is the reciprocal of F. The reciprocal of this now, I don't know how, it depends how they're going to tell us to give the answer. But there it is. I got a feeling they just left it at that. It's roughly, I mean, somewhere in the ballpark of 1.6 seconds, something like that. 1.57 seconds, something like that. And in fact, that is what it is. I think they did want us to go a little bit further than that. So once you get to here, that's what T equals. T is equal to that. Pi over 2 is, I mean, there's a lot of ways to do it, and the way I work it is basically the same way you're going to be seeing it here. 1.57 seconds. So they make us do a little bit of gymnastics, but we can do it. We can do it. That was 19. Let's go. Let's go to 20. So what they're saying here for 20, a ball hung from a vertical spring oscillates in simple harmonic motion with an angular frequency, omega, that's the angular frequency of 0.5 radians per second, and an amplitude of 5 meters. What is the maximum acceleration of the ball? It's a great question. We know from times past that, we're getting acceleration. Remember we said acceleration was, at least in terms of absolute value, was like omega squared a, or negative omega squared a, cosine omega t, something like that. I don't have it in front of me right now, but I think that's the way we're working it initially. Well, the biggest value this can get is 1, so 1 times this is just this. And omega squared a is where the maximum is going to occur. So if they're talking about this, I mean, that's kind of where it's at, and that's where the A max is going to occur. So a number of ways to write this. Again, I hate erasing this stuff, guys, because it never comes out the same. But here's A max. A lot of chalk on the board, so I don't know. Hopefully, writing big enough, we can see this. So A max is going to be this. This is really where we're going. If that's the case, what's going to be the maximum acceleration that we're dealing with to get this, right? So, well, let's talk. I mean, if that's the case, then A max now they told us some stuff that kind of makes our life a little bit easier. A ball hung from a vertical spring oscillates in simple harmonic motion with an angular frequency of 0.5 radians per second and an amplitude of 5 meters. What is the maximum acceleration of the ball? So the ball is hung from a vertical spring and it oscillates in simple harmonic motion. They gave you the angular frequency, so the angular frequency is 0.5. So those units are fine. We're going to square that. The amplitude, the more amplitude we're dealing with, that's 5 meters. I think it's going to be somewhere on the order of, absolutely. So And that's 20. Let's do 21, you guys. Number 21. Let me just quickly check the sound quality, guys, really quickly if I could. There we go, we're fine. For number 21, equation of traveling waves. Find the speed of an ocean wave whose displacement is given by the equation y equals 6 cosine the quantity 4.5x minus 6.7t, where x and y are in meters and t is in seconds. We have been here before, guys. We can do this. Let's look at it. Right, this one's pretty straightforward for us, I think, actually. So let's now go to 21, and 21 we know, or they're at least giving us the equation in some, whether it's cosine or sine, folks, that's not a big deal. I mean, cosine and sine are kind of two sides of the same coin, you can say. They're not the same function, but they're basically the same function. Pick which one you want to call it, and the other one is just that same function out of phase when compared to the other one. They're out of phase with one another, that's it. They've got the exact same look to them, they're just out of phase with one another. So you can use sine or cosine. They're going along in the direction of using cosine here. Y equals a cosine kx minus omega t. Sounds good to me. They're telling us y is, the amplitude was, let me just see exactly what they're doing, guys, here. Right, find the speed of an ocean wave whose displacement is given by y equals 6 cosine 4.5x minus 6.7t, where x and y are in meters and t is in seconds, guys. They just as easily could have written this with a sine function, but you know they did. I mean, there's ways you can write things. They're not a big deal, not a big difference. It's essentially the same wave, just out of phase. One's out of phase with the other. That's it. They are telling us that y is y. 6 is 6 meters. Cosine 4.5 x minus 6.7 t. Folks, we know that omega, you know, we know a bunch of things. We know basically we know that F times lambda, which is the same as 2 pi F over 2 pi over lambda, which is equal to omega over k, which is equal to, here's, you know, here's omega, here's k, and let's deal with it. Omega is 6.7. Omega is 6.7, k is 4.5. And at the end of the day, that's going to be V. 6.7 over 4.5, it's 1.49 meters per second. Okay, guys, just in case, it should be saying this okay, I guess, and I'll just put it down here as well. V is 1.49 meters per second. In case the stuff doesn't print out okay, or at least on the film, but it should be okay for the most part. 1.49 meters per second. And that was 21. That was 21. So all right, let's proceed. Let's go to 22 and onwards. Okay. Specific heat is what they're asking about here. For problem number 22, they talk about specific heat. Object 1 has 3 times the specific heat capacity and 4 times the mass of object 2. Object 1 is given 4 times the amount of heat that object 2 is given. If the temperature of object 1 changes by an amount delta T, the change in temperature of object 2 will be, okay, now there's a lot here, guys. This is not necessarily very difficult, but we got to know, this is where we train these problems. We train to do these problems. We look at this stuff. We pay attention. We work hard. We don't try to do this stuff right when we get to class during an exam. We don't try to learn this during an exam. We learn this before an exam, and then we know how to do it. They talk, once again, I mean, object 1 has 3 times the specific heat capacity and 4 times the mass of object 2. Object 1 is given 4 times the amount of heat, in addition to all that object 2 is given. If the temperature of object 1 changes by an amount delta T, the change in temperature of object 2 will be what? Fascinating question. Well, let's talk about it. Specific heat capacity times mass times delta T will tell you the amount of heat required to change something. How much? It's kind of weird. If you have changed the temperature by this much and it's very massive and there's this specific heat capacity, this is the amount of heat that you need. Basically, you need a lot of heat if you're going to make a big temperature difference. You need a lot of heat if there's a lot of mass. C is a constant depending upon the circumstances. Well, that's interesting because the specific heat capacities are different. If there's a very big specific heat capacity, you need very much energy to change the temperature. If there's a small specific heat capacity, you don't need very much energy to change the temperature. Let's talk. They're telling us in... I just want to make sure I got my own notation straight here, guys, when we do this. So object 1, we want to see the delta T of the other one. Okay, so basically, object 1 has got a lot going on. Object 1 is given 4 times the heat that's given to object 2. So we'll say this is 1 and this is 2. Whatever's going on here. Pertains to object 1, pertains to object 2. 4 times the heat is given to object 1, and that object 1 has 3 times the specific heat capacity that object 2 has, and it's got 4 times the mass that object 2 has, and it does have a temperature difference of delta T. They didn't really say much about the delta T on that side, but I guess it's going to be a ratio. The change in temperature of object 2 will be in terms of delta T. They just said, hey, look, at the end of the day, this is the change in temperature for object 1. For object 2, it's kind of, object 1 is based on what object 2 is. So object 2 is just Q, there's a C, there's an M, and we don't know what this one is. It's delta T prime. Everything going on with the big situation where there's big numbers going on, specific heat capacity, mass, amount of heat, all the big stuff's going on with object 1. All the small stuff is smaller by a proportion of 1/4 as much heat, 1/3 the specific heat capacity, 1/4 the mass. So you can kind of gauge it. You kind of use this guy as the measuring stick and see what happens here. Look, this isn't really bad at all. What we get here is 4Q divided by Q. Let's just divide 4Q. Let's take 4Q and divide it by Q, and let's take all the top stuff. And, the Q's cancel. You got 4 over 1. The C's cancel. The M's cancel. 3 times 4 is 12. Well, these are just 1 times 1 is 1. 3 times 4 is 12. It's 12 times delta T over 1 times delta T prime. The hardest part of the whole problem right there, you guys. Once you get it to there, you're set. Let's solve for delta T prime. Let's multiply by delta T prime on each side, and then divide by 4. And what we got is we multiply by delta T prime on each side, and then divide by 4, because 4 over 1 is just 4. So we got 12 delta T over 4. Okay, we didn't need to be that rigorous about it. At the end of the day, the amount of temperature change that delta T prime is going to experience is what we just said. I mean, it comes out to here. Yeah. Very interesting. It's almost, you have to do a double take on it. If the temperature of object 1 changes by an amount delta T, the change in temperature of object 2 will be circumstances are such the temperature will change easily if there's not a lot of specific heat capacity. Also, it'll change easily if there's not much mass. So it's more likely to change. Now, granted, there's more mass here. You're doing the 4. The 4 ain't enough. The 4 times the energy put into this thing, I guess, is caught up by this. And then, so it's going to be 1/3 as much temperature. The delta T is 1/3 of what that is, or that right there. The delta T prime is 3 delta T. Okay, so a lot to be said on this stuff, guys. Pretty fascinating stuff. Let us keep going. We are looking at number 23. And let's talk about it. Number 23, specific heat. Object 1 has 4 times the specific heat capacity and 5 times the mass of object 2. Here we go again. The 2 objects are heated from the same initial temperature, T sub 0, to the same final temperature, T sub F. Okay, they're heated from the same initial temperature. They're heated from the same initial temperature to the same final temperature. What does that mean? That means delta T is the same. During this process, if object 1 absorbs heat Q, the amount of heat absorbed by object 2 will be what? Okay, does bear looking at. So we're looking at, once again, for 23, it's easier to do these than it is to talk about them sometimes. I mean, it can get a little rough to look at. Well, okay, we're comparing two different circumstances. Now, what they're trying to, I mean, it bears looking at again, because it's not, this stuff has its own challenge. Object 1 has 4 times the specific heat capacity and 5 times the mass of object 2. Okay. If you're going to change its temperature, it's going to be pretty tough. There's a lot of mass there, and there's a lot of specific heat capacity, so there's going to need a lot of heat. The two objects are heated from the same initial temperature, T0 to the same final temperature, TF. So you're bringing them both from the same starting point in terms of absolute value temperature to the same ending point in terms of absolute value temperature. They are started from the same place in temperature, and they end at the same place in temperature. One just may need a lot more work than the other to get it done. I mean, that's what we were kind of talking about. During this process, if object 1 absorbs heat Q, the amount of heat absorbed by object 2 will be what? Well, object 2 does not have the same specific heat capacity. It has a smaller specific heat capacity, and it has a smaller mass. Our gut is it doesn't need to it doesn't need to absorb as much heat to make the temperature change happen. If something is massive and a lot of mass and there's a lot of specific heat capacity, you need more Q to make it reach the delta T. If there's not a lot of mass and not a lot of specific heat capacity, you can reach that same delta T with smaller Q. So we suspect it's going to be a smaller number. When you look at this, you've got the first scenario for object 1. I'm calling it Q. Q1 is just, Q1 we'll call it Q. It's got 4 times the specific heat capacity of object 2. Object 1 does, 4 times the specific heat capacity of object 2, 5 times the mass, and there's going to be a delta T here. Q2 is going to be, initially there ain't much going on. Now, the delta T is the same in both circumstances. Why is that? Well, delta T, we said, was TF minus T sub 0. They both started here, and they both ended here. The delta T is the same. Q1 is Q, whatever you want to do. If Q1 is Q, just say Q over Q2, ratio-wise, is 4C, 5M, delta T, over CM delta T, well, we know this. I mean, we all know that. Q over Q2, 4 times 5 is 20, 20 over 1, multiplied by Q2 on each side. Well, wait a minute, maybe I don't want to do that. I want to find out what Q2 was. Let me solve for this. Let me, cross multiply or do whatever I want to do. Let me multiply by Q2 on each side and then divide by 20. Multiply by Q2 on each side and then divide by 20. Multiply by Q2 on each side and then divide by 20. Yeah, as we suspected. As we suspected. It doesn't need as much it doesn't need as much heat to make this happen. I mean, as we said it like this, I mean, the way I got it in the thing is not a big deal here. Let me just write this. It's 1/20th. It's the same thing, obviously the same thing, But we got this. With 1/20th of the heat, it'll reach the same temperature difference as the other one. Why? It's much less massive. It's got much less specific heat capacity. And that makes it happen. So that's 23, you guys. Let's do 24, 25. Okay, folks, let's keep going. We're looking pretty good. Let's do 24 and 25, and then we're done with this. For number 24, they talk about radiation. For number 24, they talk about radiation, and they say a giant star radiates energy at a rate of 3 times 10 to the 30th watts, and its surface temperature has been measured to be 3,000 Kelvin. And suppose that a smaller star of half the radius, emits energy at the same rate. Then what would its surface temperature have to be? Assume both are perfect emitters of radiation. Well, it's going to be harder for it to do it, but let's look at some of the mathematics that kind of confirms certain things. Our gut feeling is it's going to have to be a bigger temperature than the 3,000 K, but let's look at it. We know that the power is Q over T is sigma epsilon A T to the 4th. Power's got to equal power, guys, as we said. And if that's the case, if power equals power in the first scenario of what they're telling us, sigma's what it is, epsilon's what it is, 4 pi r squared is what it is for whatever radius it is, and it's 3,000 to the 4th. The other scenario is still a sigma and an epsilon, certainly. There's still a 4 pi. Yeah, but the radius is half as big, you guys. The radius is half of what it was over there. Okay, I'll keep that in mind. Don't know what this one's going to be, but because this is smaller, this is half the radius of that. It's half the radius of that. When you square half, it's a quarter. If it's a quarter, this t to the 4th has to be bigger than this t to the 4th by a factor of 4. Yeah, and if you get the 4th root of that, it's a little, so be careful. Let me not say too much here. Let's say if two things are equal, if you divide by sigma on each side, if you divide by epsilon on each side, if you divide by 4 on each side, if you divide by pi on each side, we got all this. And then you say to me, okay, hold on. We got 3,000 taken to the 4th. We got r squared here. We got t to the 4th. We don't know what it is. This squared is 1/4 r squared. Let's divide by r squared on each side. Let's divide by r squared on each side, and then let's multiply by 4 on each side. Right? We'll divide by r squared on each side, and then multiply by 4 on each side. And we got t to the 4th equals 4 Definitely equals that. Okay. Let's get the fourth root on each side. Let's get the fourth root of this. Let's get the fourth root of this product. The fourth root of this is just t. Bring it inside, it's give me the fourth root of 4, whatever that's going to be. Give me the fourth root of 3,000 taken to the fourth power. The fourth root of 3,000 taken to the fourth power is 3,000. That's the big move. I mean, we're not done, but that's one of the there's a lot of big moves you got to make, and that's one of them. Grind that out, you guys. And you got 4,242, 4,242.6 K. We suspected it had to be a greater surface temperature than what we had for that kind of power output to come out, for it to be equal to the star that had the bigger area where this was happening. And there you go. And there you go. Just checking the sound quality, guys, real quick here. All right, let's do 25. 25. Simple harmonic motion. For number 25, simple harmonic motion, the position of an air track cart that is oscillating on a spring is given by the equation x equals 12.4 centimeters times the cosine of the quantity 6.35 radians per second times t. At what value of t after t equals 0 seconds is the cart first located at x equals 6.2 centimeters? Please note that here t is in seconds and angles are in radians. Typically, unless they tell you otherwise, when you're dealing with wave equations, you're typically dealing with radians per second squared, whatever you want to be dealing with here. But it's the radian that rules the day there. Unless they're somehow explicitly talking about something in another way. Even then, you're frequently converting to radians. Always work under the assumption that it's radians, okay, when it's a problem like that. Well, I mean, they said a lot here. Let's, apparently it's a lot easier than maybe it sounds. They're basically saying, the position of an air track cart that is oscillating on a spring is given by the equation x equals 12.4 centimeters cosine of that quantity, 6.35 radians per second, times t. At what value of t after t equals 0 seconds is the cart first located at x equals 6.2? This is all easier done than said, guys. So let's kind of just go there. So they're giving us this equation. Let me just kind of, it's almost more, if you already know it's, just know that you're dealing with radians. That's why they were pretty explicit about radians per second. If you know that, you can get rid of the clutter of radians per second, as long as you know that it's radians per second. As long as you know it's radians we're talking about, radians per second that we're talking about. The fact that it's centimeters is not a big deal, because in the end the answer is going to be centimeters as well. They're telling us basically there is simple harmonic motion taking place, and it's taking place in the following manner. X is 12.4 cosine 6.35, and we're talking about radians, so we're okay there. And we get to here. That's what it is. They're asking simply, when will this thing, this is 12.4 centimeters, when will it be at 6.2? When x is 6.2, it'll be at 6.2. So write 6.2 right here. If something doesn't pop out at us right now, let's explicitly say it. 6.2 is half as big as 12.4. Divide by 12.4 on each side, and you got 0.5. You got this. Now, at this point, guys, let's keep going with this. I mean, once we get to here, let's get up there and keep going, right? So if 0.5 is equal to the cosine of 6.35t, that's what I just said here, right? That's what I just said here. Now I'm going up here. So we're going over here. And get the inverse cosine of 0.5 in radians, and get the inverse cosine of the cosine in radians. And these are in radians. It's going to be in radians. The inverse cosine of the cosine of this. The inverse cosine of the cosine of this is this. Equals the inverse cosine of 0.5. In radians, though. That answer's got to be in radians. And it will be. You got to set your calculator to radians when it gives it to you. The inverse cosine of 0.5 is actually 60 degrees in degree measures. The inverse cosine, let's put it this way: the cosine of 60 degrees is 0.5. So the inverse cosine of 0.5 comes from 60 degrees. 60 degrees is 1/3 of pi. On your calculator, it can spit out the answers a number of ways, but it should be something on that order, 1 point something. When you divide by 6.35 on each side, you got pi divided by 6.35 times 3. Looking like that, guys. At the end of the day, what is that? That's a good question. This is somewhere on the order of pi is 3 point something. 3 times this, is somewhere close to it's somewhere close to 20. 3 over 20 is about 0.15 or something like that. Well, yeah, comes in the ballpark of that, I guess. T is 0.165 seconds. But again, make sure you're dealing with radians when you're doing this. They made that pretty clear to us. 1.65 seconds. There it is. Okay. If you have stuck it out over the 3 films, we have done 75 problems. It's a lot of stuff, a lot of just basic stuff. It's not excessively difficult. It's a little bit on the tedious side, as you can see. And all of the answers scroll at the end of each one of the 3 videos. All 3 videos together contain all 75 problems. 25 problems from exam number 1 in video 1. 25 problems from exam number 2 from video 2, and for video 3 or part 3 or film 3, whatever you want to call them, all 25 problems from exam number 3. Okay, and it's all there. So Thank you for doing this, for watching this, and good luck to you. Take care.